Okay, this is Basic Statistics 260. We are looking at Chapter 5, specifically the third section, 5.3. So we're looking at characteristics of a binomial experiment. And my last class had an interesting mnemonic to remember this. Sippy, sippy. So what does sippy mean? Well, this one, Y, is a yes-no question, meaning it's all or nothing. It's this or that. So no in between, no 3 choices or 4 choices. It's yes or no, win or loss. Let's work our way back up. P was probability remains constant. I, independent events, and independent, we're looking for the word random usually. Simple random sample, SRS. All right. And then S, the very first thing, is a set number of trials. So those are the 4 criteria that you have to meet in order for it to be a binomial experiment, all right? And so then we could do the properties of a binomial experiment. This would be, let me show you here. P of X is equal to the combination of n items taken X at a time, and then the probability of that occurring to the X power, and then the probability against that occurring, or the probability of not occurring. So these will always add up to 1, and then X is n minus X power. So this is what the probability looks like in a binomial experiment. All right. So let's take a look at a couple of problems. A coin is tossed 12 times. Find the probability that exactly 5 of the times it lands on heads. Now this would be really quite lengthy to figure out, like, all of them. We've done it where we toss a coin 3 times and it's like 8 possible outcomes, right? Well, if we toss it 12 times, it's exponential. So it keeps, it's 2 to the first, that's 2. 2 to the second, that's 4. 2 to the third, that's 8. That's what we did with 8. Think of 2 to the 12. Let's go 2 to the 12th would be 4,096 possible outcomes. We do not want to write out 4,096 different outcomes and then figure out how many of those, the probability 5 times 5, exactly 5 heads you got out of the 12 tosses. That would be a nightmare. So we're going to use this formula to figure it out. So let's do that. So we're looking on what page are we on here? 1, 2, 3, page 4. So page 4 on the bottom under examples. So a coin is tossed 12 times. Find the probability exactly 5 will be heads. All right, so here's our probability of that occurring. It would be 12 is the number of trials. Choose 5. So a combination of 12 items taken 5 at a time. And then the probability of it occurring, well, the probability of getting heads when you flip a coin is 1/2. So that means the probability of not heads or tails is also 1/2. All right. So I usually do these in stages. So I write it down like that. I put down the probability. These should always add up to 1. And now this one is 5 times. And then this one is 12 minus 5, 7 times. So when we do the combination, 12 items taken 5 at a time, that's 792. And then this, 0.5 to the 5th power, is 0.03125. And 0.5 to the 7th power is 0.007. And 7, 8 will go. And then we multiply all that out, and that's our probability. So the probability of getting exactly 5 heads when you flip a coin 12 times is almost 20%, 0.1934. And so we'll make it 0.193 for our probability. All right. Let's take a look. The next one, a recent survey found that 23% of all drivers have been involved in an accident. Find the probability that among 7 of your 7 driving friends, exactly 2 had accidents. All right, so we can do this. This is a binomial experiment. Let's run through the SIPI. So first, is there a set number of trials? Yes, there's 7. 7 friends that you have. Are they independent? Simple random sample. All right, so we're assuming independence. That that you're not friends with all bad drivers or something like that. That it's a pretty random sampling of friends. Probability remains constant. That is set at 23%. And is it a yes/no question? Yeah, it's either have you had an accident or have you not. So let's set it up. Seven, choose 2, 23%, and now always jump to here, and this is 1 minus 0.23, so that's 0.77. And then the 2 goes here, it always goes in the first probability, and then this one is going to be 7 minus 2, so that's 5. So a couple of things, whenever I set these up, I always make sure this and this add up to 1, and I always make sure this and this add up to the 7. All right, and so 7 choose 2, there's only 21 ways that can happen. And then this is 0.0529, this is 0.27068. And we multiply all that out, and that's our probability. There is about a 30% chance. We'll call it 0.301. Okay. A competing study found that 37% of all drivers have been involved in a car accident. Find the probability among your 7 driving friends, 3 or fewer have been in accidents. Oof. So this is going to be a little tougher because we're going to keep this in the bank here, the 7 choose 2. I'm going to erase SIPI. It's still a binomial experiment, but now there's an or factor added to it, meaning 3 or fewer means 3 or 4, no, 3 or 2 or 1 or 0. So that means we have to find each one of those and then add them all together. So 3, that's going to be 7 choose 3, 0.23 to the 3rd. This is a 37. Oops, sorry. Oh man, then we don't get to use this because they changed I thought it was the same probability. It's 37%, not 23%. So we don't get to use this. I can erase that. All right, so it's 37 there, which means that's 63 there. So 3 and 4. So that's exactly 3 of your friends. But then we also have to calculate exactly 2 of your friends with different percents. So notice that and that, same work, only this has been changed. All right? Which is going to change our whole answer. So we don't get to recycle 0.30. Or one of them. or 0 of them? So remember, anything to the 0 power is 1. All right? So let's do this. This works out to be 0.279. This works out to be 0.285. This works out to be 0.162, and this works out to be 0.039. So when we add all of those up, the chances that 3 or 2 or 1 or none of your friends had an accident, given 37% chance of it occurring, that would be about 77%, 0.76. I think it's worth mentioning here. Look, if you had 7 Blu-ray discs, and I said you can bring 0 along on the trip, how many ways can that be done? Well, that's 1. It's one way. You're leaving them all behind. Anything to the 0 power is 1, and 0.63 to the 7th power. So think about what's going on there. This is none of your friends had an accident, and all 7 of them didn't. Well, there's a 63% chance that all 7 of them, like per person, had it. So it's sort of an and problem, where your first friend hasn't had an accident, and your second friend hasn't had an accident, and your third friend hasn't had an accident. So it's 0.63 times 0.63 times 0.63 7 times in a row. So that's actually how that one plays out. It still works in the formula that they've devised for binomial experiments, but I just thought that's interesting to look at. Okay, so let's finish up here. The mean is the expected amount, so that's just whatever the probability they give you times the number of people you're working off of. So if we wanted the mean of this, we would have taken 37%, 0.37 times 7. That's how many friends I would have expected to have had an accident. All right, so the mean is just n times p, the number times the probability. The variance is, that's, remember, sigma squared. That is n times p times q. And then that means the standard deviation is just the square root of n times p times q. And so here, let's do an example of that. In an interesting casino game, you roll a die and win if 2 comes up. Okay, that's a pretty easy game. If the casino has 480 players in one night, find the mean, the variance, and the standard deviation. All right, so let's do that. The mean would just be 480, and we're worried about winners. That would just be 1 times 1/6. 1/6 of the time. A 2 will come up when you roll a die, and so that would just be 80. So 480 people play, and you had to pay out 80 times, 80 winners. To find the variance, that doesn't have much meaning for us. Standard deviation does, but variance does not. So we'll do it though. That's just going to be 480 times 1/6 times 5/6. And so that's going to be 66.6, repeating forever. We'll just call it 0.67. And then the standard deviation, that does have some significance for us. So we take the square root of the 66.67, and that gives us 8.165. So what we can do with that is say 80 is the mean, and we could add 2 standard deviations up and 2 standard deviations down, and kind of set 95% of the time on such nights, you'll have between about 64 and 96 players win. So the casino expects 80 people to win. What do these numbers mean? This means the casino expects 80 people to win and 400 to lose when 480 people play on an average night. If we apply the 68, 95, 99.7% rule, that means we could add 2 standard deviations above the mean, about 16 onto that. That's our 96, and take 16 away from that, and that is about 64. And so 95% of the time, we could expect between 64 to 96 players win out of 480. All right? Okay. So let's look at another example. A recent survey, 72 graduates from METC found employment within their field of study. All right, woo, go METC. Find the probability distribution of the number of people from this class of 7 that will be employed in their field of study. And calculate the mean from that probability distribution. Okay, so we're going to do a workup then like this. So that'll be 7 choose 0, 7 choose 1, 7 choose 2, 7 choose 3, all the way up to 7 choose 7. All right? So the same kind of setup, but we're going to do a probability distribution for it. And so 0, 1, 2, 3, 4, 5, 6, and 7 people. And so we're looking at a very small number. We're only looking at 7. We've got thousands of students at METC, but we're keeping it small so these numbers don't get ridiculously horrible. So just so you know what's happening here, each one of these I'm going to make a probability based on this. So this would be 7 choose 0 and 0.72 to the 0 power and 0.28 to the 7th power. And that would be 0.0001. So it's not very likely that none of the 7 randomly chosen out of a group would not be employed. It can happen, but it's really unlikely. 0.01% chance of that occurring. That none of them actually have a job. How about just one of them? So then we would do this. 7 choose 1, 0.721, 0.286. And so that ends up to be 0.002. And so we just keep going up the ladder here. I'm just going to put in the answers: 0.019, 0.08, 0.206, 0.319, 0.273, and 0.100. All right? Okay. So calculate the mean from this probability distribution. So the mean from a probability distribution, remember how we do the mean of a distribution like that. We take this and multiply it by that, and then just keep adding them up. So let's do that. So that is the summation of x times the probability of x. And so that's going to be 0 plus 0.002 plus 0.038 plus 0.24 plus 0.824 plus 1.595 plus 1.638 plus 0.7. That is 5.037 if we did it that way. All right? Using a probability distribution. Let's calculate the mean just using our simple, from the formulas above. So look, the mean should be equivalent to n times p. That would have been 7 times 0.72, which is 5.04. This way seems a lot easier, doesn't it? We just take the 7 times the 0.72 instead of doing all of those calculations and finding the mean. Let's find the variance. Would just be 7 times 0.72 times 0.28. And so that means the variance would be 1.4112. And then the standard deviation, that's what we're kind of after usually. We're usually not too worried about the variance. We're worried about the standard deviation. That's 1.188. So about 1.2. Okay. So yeah, this method much, much easier than doing it the long way. All right, so let's see what they got here. Calculate the mean of this binomial distribution using a formula and calculate the variance and standard deviation from the number of people from the class who will be employed in the field of study. Okay, we did that. I did all the work on that page before for that. Example, in a poker hand, find the probability of getting 4 of a kind. Okay, so this is now, that's not a binomial distribution. Remember, SIPI, it has to be a yes-no question. This is a yes-no question. It's getting 4 of a kind when dealing out cards. So this is just a probability problem. So we'll take a look at that quick, but this is not a binomial. So we're on the last page of the notes for chapter 5, not binomial. Experiment. So the probability of 4 of a kind. So how many ways can that happen? That would be like ace, 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 2, 2, 2, 3, 3, 3, 4, 4, 4, 5, 5, 5. So pick a repeated card, pick the 5th card. So there's basically how many ways can I get, how many distinct ways can I get 4 of a kind? Well, there's 13 ways to get it, you know, ace, 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 2, 2, 2, 3, 3, 3, 4, 4, 4, 5, 5, 5, 6, 6, 6, all the way up. So that's where the 13 comes from. But then it's times 48 other cards. Because 4 of them are taken. There's a deck of 52 cards. So let's pretend I get all 4s. So I get a 4, 4, 4, 4. But then there's 48 other possible cards for that last position. So there's 13 ways to get, you know, a repeated card 4 times. And then 48 ways for the leftover card. And so that amounts to 624 total possible combinations of 4 of a kind hands with 5 cards in your hand. So we do that. So 624 hands would be 4 of a kind out of every possible hand, which we did in the past. That was a combination of 52, choose 5, which is a really large number. And so when we divide those two, we end up with a not very likely scenario. Less than 0.02% of a chance. So that isn't 2% chance, it's 0.02, less than 1% chance. All right. Okay, in American Roulette, the wheel has 0, 0, 0, 0, or 0 and 0, 0, and then 1 through 36. So 38 possible. If you bet my favorite birthday, 21, 10 times in a row, what is the probability you will win exactly 1? This is a binomial problem. So that is 10, choose 1. What are the chances that you will get it? That's 1 out of 38. I'll tell you what, we'll make 1 out of 38 into a decimal, 0.026. You can leave it 1/38 if you want and 37/38, but I'll make it into a decimal. I think most students have an easier time wrapping their head around decimals. And then there's a 97 7.4% chance you're going to lose. It's much more likely to lose than win, with 1 out of 38 as your chance. All right? And so we figure that out, and we get 0.205. So that's about a 21% chance. If you do it with the actual fractions, instead, this is actually a little more precise, then you will get 0.207. So that is round off error. That's why it's 2 thousandths off on one of them than the other one. All right. What is the probability you win at least once? Okay, so instead of figuring out 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10, it is much easier to go the other way and just say 1 minus the probability of not winning, no wins. Because that's the only one in our sample space that isn't covered. Look, if you play 10 times, the roulette wheel 10 times, one, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 11 possible outcomes. Right? But instead of figuring out 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9 or all 10 wins and add them up, it's easier just to figure this one out and then subtract it from 1. They're complements. So we're going to figure out the probability of no wins. So 10, choose 0, 1/38 to the 0, 37/38 to the 10, and that turns out to be 0.766. So 1 minus 0.766 is 0.234. So you got about a 23% chance you'll win at least once. That's not that great with 10 plays. Not even half. So, all right. So that is chapter 5 in a nutshell. I hope everybody gets it. We'll see you next time on chapter 6.